Okay, let's get started. All right, so I noticed a few of the muddiest points asked about. Let me see if I can turn on the other screen. I'm not sure why that's not on right now. Sorry for those online. One of the two projectors is off for some reason. So just trying to get it back on for those in person. All right, looks like we might just be stuck off. Okay, so it looks like we only have this one screen over here today because that projector refuses to turn on right now. So sorry about that for those over there. I was looking through the muddiest points from this week, kind of finally, getting down through them, and noticed some folks had some questions about entropy and why we use the logarithm in entropy. And I posted in the discussion boards and kind of a longer answer to that. The short answer for why you use entropy in these calculations, without getting to the base, is that if you consider that a system A has some number of states, I'll say n microstates, and then you consider another system B has some number of microstates, we'll say m microstates. If you were to combine those two systems in a combined system A plus B, then the number of microstates for the combined system would be the product of those, n times m. So in other words, for every possible microstate system A could be in, system B could be in any of its microstates. And so the total number of microstates in the combined system is the product of the two. And so we would like entropy to have this property that if you know the entropy of one system and you combine it with another system, that their entropies combine. And that is the primary reason why entropy has this logarithmic flavor, because you want to make it so that we know that kind of the log of m times n is going to be log m plus log n. So entropy is based on the number of microstates accessible in a system. And so when you add two systems together, the product of those microstates is what you get as the result. So if we define entropy as the log of something that has to do with the numerosity of the number of microstates in a system, then we have this convenient property that entropy is going to add. So you mix two systems and you get an add from their entropy. So that's part of the reason we use log. And then as I talk about in the discussion board, if we view entropy as the amount of information left in a distribution after you fix the distribution, so we know that the particles in this room are going to be, in a little ball in the corner, then there's a lot of, there's uncertainty left in the ball, but that's not outside the ball. So we've reduced the amount of uncertainty. Then we can still quantify how much uncertainty is left. And it's often convenient to do that and sort of saying, how many bits of information would I need at a minimum to communicate the amount of information that is left over. So if I actually figured out what the microstate was inside that little ball, then how many bits of information would I need to communicate to you? And if and log base 2 sort of actually gives us a nice metric for that. So there was a reason why in information theory we use log base 2, but the reason we use logarithms in general is due to this multiplicative property. So for more info, see discussion post on Canvas, as well as ed discussion in Slack for more info. Okay. So nominally today, and I'm just going to wander back over here for a second to see if there's a remote. Maybe I can force that projector to come on because it feels very lopsided in this room, only having the one projector. But I think unless I was to crawl up onto the table there and just manually jab at it, I think we're just stuck with the left display being off. Let me double check something here. Yeah. All right, so I guess we'll just have to work with this. You guys see, I mean, if you guys would rather move, it's fine with that too. But I mean, it's fine not. I don't want to force you to, but I just feel like if it were me, it seems like that's a funny angle. But maybe it's fine from back there. All right. Well, anyways, so we're about to start onto the swarm intelligence and distributed AI topics, but I want to finish up. We didn't quite get to the end of simulated annealing, so. Just to put us, this is a quick reminder, and I actually dropped a variable in one of my explanations last time, which I don't know if will help or not, but if we think about the law of large numbers, which I'll otherwise call LLN, the law of large numbers basically says that if you sample a function, so if I take a bunch of points and I run them through a function, so if I say I've got like f of x1 plus f of x2, where these x's are my samples, and I take the simple average of them, then the law of large numbers says as m goes to infinity, then this goes to the integral of your function times your sampling distribution. So this here is your sampling distribution. And these are your samples. And this is the function, So so that's the simple law of large numbers. And so in conventional Monte Carlo methods, you assume uniform sampling. So if we have uniform sampling, then your density is just basically 1 over, and I'm going to say L here, where this is the volume of the sample space. And so if I'm sampling along a one-dimensional line, just taking samples across there, then L is the length of the line. In other words, what this is saying here is that X comes from a uniform distribution between some A and B, where L is equal to B minus A. Or if it's easier, you can just say this is like similar to saying we're sampling from 0 to L. So we sample uniformly from 0 to L, and we take these random samples, we plug them into our function, and we compute this average. And if we have enough points, the law of large numbers, which is related to the central limit theorem, says that this thing will converge to this integral right over here. That's just the standard law of large numbers. Now, if we plug in this density, 1 over L, then that integral becomes our function, and I'm going to pull the 1 over L out. And this, so this is exactly the same here as I have up here, but I've just plugged in the P of X. And so if I were to say, well, I'll take this P of X here, plug in the 1 over L, and then the result gives me this down here. So that thing right there, we're saying is approximately equal to the thing that I've got up there on the left, which I could rewrite. I'll do in a kind of more compact form here. Which, with a little rearrangement, I multiply both sides by L. And what I get then is that the integral of my function f of x is approximated by L divided by M times this sum. And so this allows us to do, this is so-called Monte Carlo integration. And if you think back to your first calculus course, this should look somewhat similar to Riemann integrals, where you're chopping up an integral into little rectangles of length L over M. What is different here is that in the Riemann integral, you actually partition the line so that those rectangles are guaranteed to be jammed up against each other. Here, we're kind of fudging it a little bit, where we're just saying we're going to draw uniformly. So on average, these rectangles are going to be right up against each other, but some rectangles are going to overlap a little bit. Some rectangles are going to have some gaps. But this is basically a random approximation of Riemann integration, where instead of laying down the rectangles right next to each other, you allow the rectangles a little bit of overlap. That's all Monte Carlo integration is. And that's fine, but for if there are regions of your f of x function that you're trying to integrate under that are really small, then you kind of waste a bunch of samples. And so in order to sort of get a really good, in order to get sort of the area underneath this curve, you kind of want to concentrate your sampling effort underneath the curve. So if there's a bunch of regions of the curve which are close to zero, then you're kind of wasting a bunch of the samples in that area. You need them for this method to work, but you're going to need a lot of samples in order for this approximation to work. And so, I'm just going to emphasize here that this approximation assumes M is going to infinity. So a large number of samples. So for fx small regions that are small, need large M. Okay, so that's Monte Carlo integration. Now, what these physical chemists were realizing is that they needed sort of the more fundamental version of the law of large numbers up here. They needed to take not just an area underneath the curve, because really, if I wanted to solve any expectation problem is solving for an area underneath the curve. So in general, if you give me an equation of a microstate, an equation of state, and you tell me that I want a Boltzmann distribution right here, so forget about it being a sampling distribution. So if I think of f of x, so down here, I guess I focus on, if I focus on this thing down here, I can put whatever function I want there, and this f of x could be my equation of state times the Boltzmann distribution, and I could take the integral underneath that curve. Fine. That's one way I could solve this complicated problem. But if my Boltzmann function has a very small density out at its tail, then there's a bunch of microstates that I'm sampling from that I don't actually really need to calculate the area underneath that curve. So, so we can go back and think the more fundamental version up here. So that's really what Metropolis was trying to do, is he's focusing on, again, the law of large numbers says that the integral of any function is approximated by the function, samples of the function, where x is distributed according to this probability density function. So in Metropolis's case, this is the Boltzmann distribution. So this more refined version is just making more, instead of taking the law of large numbers and rearranging it to get this kind of Riemann integration looking thing, then I just go straight back to the old fashioned, this pure version of the law of large numbers. And it just says that if I can manage to sample, instead of sampling uniformly, I'm going to sample according to the Boltzmann. And if I do that, then I can use this simple average, and this simple average will converge to that integral, which is just, again, that integral is the expected value over that distribution of the function that I'm trying. So the x here, this is a microstate. The little f, that's a distro of microstates, which is the Boltzmann in this case. And big F, that is our equation of state. You can think of it as a macro state, I guess, macro state property. And you can think, for example, pressure, et cetera. Yeah, pressure, et cetera. So we want to take the average of that equation over the distribution of microstates. We can use the law of large numbers for that. All that we need computationally is this, how to sample from any distribution. We know how to sample from a uniform distribution. How do we sample from, say, the Boltzmann distribution? And that's what ultimately is where the Metropolis Hastings algorithm came from, which we talked about last time. I guess I'll just start there. And so the Metropolis Hastings is a generalization of the original Metropolis algorithm. So, to sample from an arbitrary distribution, we can use Metropolis Hastings algorithm. And we could view this as basically the first MCMC, Markov Chain Monte Carlo sampler. And the Metropolis Hastings algorithm is a pretty simple form. We are going to generate a candidate sample randomly, however you like, generate a proposed improved sample. So I'll call this sample X, and I'll call this improved sample Y, which I can choose how to do that. So I can create some sampling distribution that is going to be based on the existing X. And so I choose, so this is kind of like a random walk. So an example here might be that G of Y given X is equal to whatever the existing X was, plus some noise that has zero mean and some variance. So that would allow me to kind of walk around the space. And so I start in one spot, and then I propose that this new spot is better, and then I evaluate that. And so in part 3, then I calculate an acceptance ratio. Which I'll call alpha, and I'll call it F of Y divided by F of X. So this here is a likelihood ratio. And for where F is desired distro. And so if F is Boltzmann, then the acceptance ratio alpha is just equal to the exponential minus, I'll call this delta, I'll just call it minus delta for now, and then I'll just find that in just a second. Minus delta over KT, where delta is equal to y minus x. And then from that acceptance ratio, I can decide whether to take x or y. So basically, if alpha is greater than or equal to 1, take y as sample. Otherwise, take x as sample. Or sorry, otherwise take y as sample with probability alpha. And then otherwise x. And then finally repeat from number 2. And so it's just a random walk where we start in a particular position that has a particular probability density, f of x. We step into another position. If we have stepped into a position that has higher density, then we go there. If we step into a position that has lower density, then we might go there, but we're going to flip a coin to decide if we go there. And so we go in there with some probability. And that is the Metropolis Hastings algorithm. And if you do that, then like I sort of said here, after an initial transient, which I'm going to call a mixing time, samples will be distributed as desired. And the beauty of this algorithm is, one of the beauties of this algorithm is that this f function here, I've been calling it a density, it only has to be proportional to the density. So if you can build a model of your desired sampling distribution, but you don't actually want to go through the process of properly normalizing it to make it a real probability density function, so the area underneath it is equal to 1, that's fine. F just only has to be proportional to the desired density function. And that's one of the reasons why the Metropolis Hastings algorithm has become so powerful in Bayesian analysis, where you have to calculate these posterior probability distributions, as well as a number of other, say, modeling contexts, where you need to build models of systems where you know how to build sort of relationships among the densities of different outcomes, but you may not know the actual shape of the entire probability density function. And in order to do so would be a numerical challenge in itself, because you'd have to integrate under the whole probability density function, and we're back to numerical integration. So you'd have to run a giant, ugly numerical integration problem first, before then you run into this thing, which might actually be used in another numerical integration problem. So that's what's great about this, is that you don't actually need to know the densities themselves. So that's Metropolis Hastings. So this empowers us to sample from any distribution we like. So, and originally just from the Boltzmann distribution. So simulated annealing, the thought was, well, great. What Kirkpatrick realized is, he said, that most of these optimization problems can be viewed as in the same ballpark as what's going on inside a physical system as it's trying to minimize its energy. So it's kind of like in the physical system, if you can reach a lower energy level, you always go down to that energy level, but you occasionally pop up to higher energy levels. So there's enough kinetic energy inside a system that it has the ability to go up its energy to higher energy potentials. but then it'll have less kinetic energy available when it goes up to there. It sort of borrows from its kinetic energy to get up there. But if you can go down to lower potential energy, you definitely will go down to lower potential energy. And so that sort of suggests that what's going on inside matter is a type of optimization process that we can mimic. And that's what, simulated annealing comes from. And so in the Kirkpatrick et al. Science paper, then what they did is they basically used the standard Metropolis algorithm with varying temperature to optimize high dimensional systems. And so what did that look like? Well, so I mentioned last time, well, what's the mapping here? And so, and I've mentioned this a couple of different times right here, but the position of molecules or atoms or whatever your microstates are inside a piece of matter, that's like a high dimensional configuration variable for an engineering design optimization problem. So in the physics, the many degrees of freedom of position and momentum for every particle maps to a decision vector where you can think of variables as the properties of individual particles. So in the example that I posted in the discussion, when someone asked about the log base 2, I gave the example of a system that we might be optimizing where we have 4 binary decision variables. Each one of them is either 1 or 0. Well, those 4 binary decision variables, each one of being 1 or 0, it's kind of like having 4 particles in a small chunk of matter in each, and then those different 1s or 0s, those could be the different positions of those 4 particles as they're in this chunk of matter, or they could be the different momenta. So one of the particles is in motion, the other one isn't, the other one is, the other one isn't. So the 1 zeros might have to do with the momentum of these particles. And so there are a bunch of different ways we can have the momenta of the particles in this chair. Some of them are in motion, some of them are not. We can also think, well, wow, this chair's got a gazillion of these atoms that are jiggling, some jiggling and some not. Well, this is a model for thinking of a decision vector that has a gazillion decision variables, each one of them either 1 or 0. So that's kind of the mapping there. So that's some from the physics side of the things. That's one of the things here. And then, so this is sort of our, so these are kind of our candidate solutions. So then the sort of the ground state. So you can think of this as the kind of lowest energy microstate. Well, that is our global optimum. So this chair, if you give it enough time, will eventually go to the maximum entropy. Well, I'm not going to use that term. Eventually, systems tend to find their lowest energy. It might take them a long amount of time, but they eventually find that lowest energy. So the books on your bookshelf are being held up there, but they'd rather be on the floor. If you don't potentially keep looking at your bookshelf and maybe fixing little nicks in one of them, eventually those books are going to break the bookshelf and the books are going to fall to the floor. They eventually will find the floor. That is the lowest energy configuration, the books on the floor. We're holding them away from that by putting up that bookshelf. And that's the idea here. We want to be able to find that ground state in using simulated annealing to do that. And so so the process of, so the movement from one microstate to another, that maps to the generation of new candidate solutions. And this is where temperature is important, because temperature, that's what we call it in the physical world, but in the optimization space, it's just a fancy name for the kind of maximum allowable movement we're allowed from a current candidate solution and the next candidate solution. So when we heat our simulated system up, all we're doing is we're saying we're giving you a budget where we're allowing you to explore farther in your random walk. So the random walk around the configuration space for simulated annealing, the steps of the random walk are governed by the temperature of the simulated material. And so that's when we talk about temperature, that's what we kind of mean there. So this is kind of the rough outline of the inspiration behind simulated annealing. And so how then does simulated annealing, what does that kind of algorithm look like? Well, basically, we'll say the SA algorithm pseudocode. Like most meta-heuristics, you know, it has a similar feeling, but remember, this is not a population-based meta-heuristic. So our first step here is we are going to generate an initial solution randomly. Doesn't actually matter what we mean by randomly there, uniformly, whatever, just some uniform microstate. And then evaluate its, and I think the term Kirkpatrick uses fitness. I don't like to use that term, and because we've talked about maximizing fitness. In this case, this is a minimization problem. So I guess I should mention here, we're trying to minimize objective function, and I'll just say, I'll call it F, capital F. We're trying to minimize this function, just like you're trying to minimize energy. So I'm going to say evaluate, instead of evaluating its fitness, I'm going to say and evaluate F at the candidate or at the solution. Okay, so that's fine. So then we have a hyperparameter. So we're going to say let beta be the number of new solutions, I'll say new candidates, the number of new candidate solutions until thermal equilibrium. Now, what do I mean by that? I'll put thermal equilibrium. This is me just saying, we're going to do rounds of simulated annealing at different temperatures. This is how long each round is. This is length of each round of simulated, I'll say of round of Metropolis at temperature T. Or in this case, we're actually going to, I'll say at temperature. I'm not going to use T as the temperature variable here because I don't want to use a K. So the idea here is we're going to set a temperature, we're going to let it running for about beta rounds, Then we're going to lower the temperature, let it run for another beta rounds, lower the temperature, run it for another beta rounds, and so on. So beta is how long we allow the algorithm to run. So again, this is a hyperparameter that you get to choose. So you choose. Okay, and now we get into the actual loop here. And so while not termination condition, and this termination condition could be based on temperature. So this could be based on temp, and we'll see where temp comes in play here in just a second. We're going to then iterate. I'll say for I is equal to 1 to beta. And we are going to generate new, so write it out, new candidate solution. And then if, I'd say, and evaluate F at the new solution. If F, and then maybe I'll just define here. I'm going to say that delta F is equal to F new minus F current. So then if delta F is, when it F new, so if my delta F is less than 0, then I take new as a candidate. So I keep new. Otherwise, if delta F is greater than or equal to 0, then we keep new with probability exponential minus delta F divided by lambda. Let me just make sure that that is the notation that I've used elsewhere. Yeah. Where lambda is our temperature. So rather than having this KT, where this K is proportionality constant, I'm just using this lambda as my, my virtual temperature here. So this lambda is my temperature. And we'll talk about how I set lambda in a moment here. And then I go to my next I, and then I decrease temperature lambda, and according to some schedule, and I'll show you some schedules in a second. And that's pretty much it. So then we say end while and report solution. All right, so that's the basic simulated annealing algorithm. We still have to address what I mean by adjust lambda according to schedule. And so I'll give you some ideas from that here too. So so I guess another important hyperparameter up here is choosing an initial temperature. All right, so let's see what some of those schedules would look like here. Before I get to seeing like how we adjust this, are there any questions about this? I see a question online. Any questions in class about this basic algorithm? Yeah. The question is, how are we adjusting the steps we make for random walks? So that's, when I say generate new candidate solution, this here, is just like, basically the same thing as Metropolis Hastings style. So you can choose whatever random walk you would like to put in that. So you can say that I'm going to try to jump to these different points. But what happens here is that this probability here will end up filtering out walks that are like, if I end up making a jump that is a very high energy increase, then it will be very unlikely that I'll take that jump. So there is some flexibility. There's a little bit of a hyperparameter feel here too for how you're generating these new candidate solutions. So this is a little bit interesting. It's like you might think of it as like, and I might have even presented it this way: at high temperatures, I take giant leaps, and at low temperatures, I take small leaps. That's not actually what's happening here. At all temperatures, I'm attempting the same leaps, but I'm filtering out, I'm allowing certain leaps at higher temperatures that are being filtered out at lower temperatures. Does that make sense? Let me see. And then online question: can we take the F current instead of the F new with probability? So I think the question is, did I say keep new with probability? I think I wrote that correctly here, that keep new with probability this. The idea here is that if the new, so remember, I'm trying to recall, minimization is goal. So that's the reason why if new is less than current, I keep it. And then here we're saying if new is greater than current, then we keep it based on how much greater it is. If it's much, much, much greater, then this exponential is going to be small because of the negative sign right here. So that's why it's keep new with this probability. If that answers the question, I don't see any chatter on there. Think that got a response. Got it. Okay, good. All right, so now all that's left here. So of course, there's a lot of flexibility. Initial temperature, how you're going to generate this candidate solution, and then this annealing schedule. So what does that annealing schedule might look like? There's a bunch of different options that you could pick, but some two common ones. Annealing schedule for lambda temperature. And so, we're going to stay at lambda for beta steps. And then after we stay at lambda, then we decrease lambda, and we could do it a couple of different ways. We could say that the lambda new maybe is equal to the lambda current minus some alpha times time, where this is the step number, for example. Or not step number, but I could say, this is like the temp. I don't want to confuse things with these steps here, but I could say round number. Of course, oh, right. Actually, I'm sorry, and I wrote that incorrectly. This I meant to be a constant. So this here, this is my initial temperature. All right, so this is saying here that you start at round 0, this isn't there, and you start at this temperature, and then at round 1, you decrease linearly. So it's a nice linear decrease in your temperature. And then so if you run, you can either run until, you could basically say, in your termination condition, I want to run this until the new temperature goes all the way to 0, or I could run it until the temperature hits a particular point that we'll talk about in a second here, why you might not want to run it all the way to where your temperature is equal to 0. So that's one way we could do it. That's kind of a nice linear schedule. An alternative is we could say that the new temperature is, it's a little more multiplicative to Clay, where I'm going to say it's my initial temperature times some alpha to the t. And so this is a little bit more asymptotic decline. So this one here will rapidly, I'll say this one here rapidly reaches 0. Whereas this one here starts fast, but then slows. And so you might, this schedule that you get for this kind of has a burst of exploration initially, where you're just searching all the way over the space, and then it kind of rapidly cools, but then it doesn't freeze immediately after that. After an initial kind of rapid cooling period, then it stays at some non-zero temperature for a very long amount of time. So the hope here is that you could adjust this so that you find that global dip in this kind of energetic landscape. So remember, like we've got kind of drawing this, we've got this f function that we're trying to minimize, and it's some sort of landscape that looks like this. And this is our x value. And so the goal is to sort of sweep over this thing and find this point, and you get stuck somewhere on this point, and then at the temperatures that are lower but non-zero, you still have enough movement where you can kind of, if there's a bunch of other tiny little pits and pots inside here, you can get over those, but then you'll gradually still make it down the landscape into the bottom here. So it's kind of like high temperatures allow you to get over. So high temps get over tall hills. Low temps, allow smooth movement over rough surfaces. So you jump around erratically initially, and then you cool down, and then you just kind of try not to get caught in any of these small patches there. And that's how you can kind of do this annealing schedule. All right, so any questions about this annealing schedule? This basic idea here. You can plug this into the back end of that simulated annealing. It's a relatively simple process where he's just calling the Metropolis algorithm over and over again with different temperatures. And as the temperatures, and over time, he lowers the temperature, and maybe you end up getting a decent solution out. And it turns out that's really kind of withstood the test of time. It's that simulated annealing tends to be a very good optimization meta-heuristic. We could talk about why that might be. And people have talked about that. So a lot of people say, like, you could do simulated annealing and you don't have to use the Metropolis algorithm. You could use Metropolis Hastings, but you could use then a different distribution here. So right now, he's saying that we're going to move our little displacements according to a Boltzmann distribution based on this delta, this is sort of the budget of how much they can kind of move upwards. But a lot of people have argued that the Boltzmann is the perfect distribution for searching because it's the least unbiased way to search. When I'm given a tiny little exploration budget of lambda, basically, I'm basically told you're allowed to move uphill and average. So that's the way to view lambda. And I guess I could write that here, is that how do we interpret lambda? And keep in mind that because the steps, remember that we've got this probability minus delta F over lambda, then what this tells me is that lambda is kind of the average change in the objective function that I am permitted to kind of average backward step. So we could think about this, lambda is the average backward step from a current candidate. So this is like how much you're allowing the thing to move backwards. And why an exponential? Well, so the exponential is the least biased. So the exponential is the least biased max entropy distribution when average is fixed and random variable is greater than or equal to 0. So basically, if you're going to make a step upwards, if you're going to make a movement in the wrong direction for purposes of search, then what this is saying is I'm going to allow you to move on average this amount. Sometimes I'll allow you to move farther than that, but it's going to be unlikely that I'm going to allow you to move much farther than this way up the optimization objective that I want to minimize. So this is how much budget I'm giving you. And then it's up to you to decide, whether how to do that otherwise. And so the reason the exponential works so well is it's sort of saying that, given this is our exploration budget, this is kind of the least biased way for us to kind of explore nearby. So it doesn't impart any biases from the programmer on which direction is best. So it might be that some programmers in their mind, they have a concept of what certain optimization objectives look like. And based on that concept, they would build a movement strategy that seems general in their heads, but is not actually general. So they would actually end up constraining the search directions based on a model of a fitness function that's in their heads. This is saying that there's no other information here. This is sort of the most honest way you can search given a search budget of lambda. That's kind of why, and that's why one of the reasons why people think that simulated annealing works so damn well for generic optimization objectives is because it is a very honest way to step through this optimization objective. All right, I see a couple of questions online, at least one. What if there are more parameters than just the temperature? I'm not sure I understand the question exactly, because the temperature isn't a parameter we're optimizing. It's a hyperparameter that is sort of changing as this algorithm runs. And so the parameters that you're optimizing are the decision variables. Those are the actual microstates. And so the things that you're actually changing with the algorithm are as you move from one microstate to another, you're moving from one candidate configuration to another candidate configuration. The temperature is just a tool for governing how far you can step from one configuration to another. There are certainly modifications to the simulated annealing algorithm where you might add in other things like that require their own parameters. I mean, I've mentioned that there's other hyperparameters here. So, we've got this beta is an important hyperparameter, how long you kind of take to reach equilibrium. You've got how you're going to generate each one of these jumps. I mean, there are these other parameters of the algorithm, but temperature is kind of the key one in simulated annealing. And you could add more, you could add embellishments. There's how dependent is this on the initial solution? So that's an interesting question. I mean, if you have an optimization objective like this one, if you initialize it here and you take small proposed steps, then, just even if all of your steps are accepted, it's going to take you a while to get all the way over to here. And so certainly having, if you have information about where an initial solution might be, it's good to have that. But a lot of times, it's not a matter of distance, it's a matter of how likely is it for you to get over barriers. And so a lot of optimization objectives that are challenging because they've got, if you're trying to minimize, they maybe have a little pocket here, and then they go way up, and then they have a giant area over here. And so this sort of optimization objective, if you initialized anyway over here, it would feel like you were moving in the right direction as you were moving closer and closer to this point here. So this is kind of a local minima, whereas this is the global, and it's in a very, very tight neighborhood. And so most gradient climbers just can't do this, because if you start anywhere, you have strong gradient information that says, it's gradient descenders, that you should be moving in this direction. And so a simulated annealing type algorithm gives you the budget where you continually allow yourself to make these movements. And then if you finally manage to get into this trap down here, it becomes very difficult to get out of the trap, which is good, because this ends up being the local, this is much better than all other solutions. So, but if you started in here initially, you have such a high temperature, it is possible that you might pop out of this trap, but it's easier to get back in the trap than get back out of the trap. And so as your temperature is lower, it's still possible you could climb up this hill and actually make it back into this trap. So, but the big thing with any of these meta heuristics, it's good to run them multiple times with different initial conditions, because the initial condition does play some role. How much of a role kind of depends on the optimization objective. It's hard to quantify that. Okay, so, okay, good. Are there any other, so this is basically where I want to leave things. This is kind of, I wanted to cover simulated annealing because it is so darn good. I guess I might also mention that simulated annealing can also be used for multimodal. And that might seem a little weird, because when I introduced multimodal optimization, I said that population-based algorithms were perfect for multimodal optimization, because you could have a population of optimizers taking up residence on all the local minima. Now, in simulated annealing, you only have one optimizer bouncing around, but if you're not depending on how your optimization objective works, if you keep your temperature from getting super cold, then it still has a possibility of hopping all around the optimization objective, and it will tend to stay in the local, in these pockets for longer than it stays elsewhere. And so you can actually use simulated annealing as a Markov Chain Monte Carlo sampler, where the sampling distribution that you're getting out is effectively the position of the local minima. So it is possible to use it as kind of a sequential sampler of the local minima. But you have to then keep temperature greater than 0 significantly. And then you hopefully can hop from some local to other local. So it's not going to be a great multimodal optimizer, but in principle, you can use it that way. And that just comes back to that simulated annealing is effectively a specialized case of MCMC, of Markov Chain Monte Carlo sampling. All right, so that's about where I want to leave it. Any questions about simulated annealing before I give you a brief intro to ant calling optimization, and then we'll pick up on swarm intelligence stuff for the next couple of lectures. All right, questions online? Okay, looks good. All right, so now moving into this new unit. So in this unit, we're focusing on either methods where we're going to give each agent, basically these are all methods. So I'm calling this distributed AI and swarm intelligence. And in this case, we're sort of inspired by systems with multiple agents that each can make individual decisions. So it's kind of redundant here. The definition of an agent is something that has agency. So rather than simulating particles that are bouncing around based on where temperature shoves them, we're actually now building systems that are inspired by multiple agents where each individual agent makes a choice, and that choice is going to be determined in part by the environment, which will be our optimization objective, and in part by whatever the heck all the other agents are doing. And so there's a social communications channel in these systems that allows an individual agent to go off and do some exploration and then somehow export her exploration to all of the other agents. So the other agents can either decide to stay in their area or to be moved closer to her because maybe she looks like she's doing a lot better than them. So it allows for a little bit of a collective intelligence here. And so there's a kind of a simplest example of this is ant colony optimization. So simple example, ant colony optimization. And this now goes by ACO, but I'm going to introduce a primitive form called ant system that was the original version. And these methods are generally attributed to somebody named Marco Dorigo, who's still around. And in some of Marco's legacy of people who come out of his lab, postdocs and grad students and so on. And so what Marco's insight is if you look, it was basically, this is inspired by a sort of simplistic model of pheromone trail following by foraging ants. Now, I study ants myself. I have ants in my lab. I have grad students who go all over the world to study all sorts of crazy things that the ants do. I can tell you that what I'm about to say is not how most ants act. There are ants that don't follow pheromone trails at all. Those that do follow pheromone trails are not so simple as this model suggests. But people in the early 80s, late 80s, got excited about simple models from the mathematicians of trail following that seemed to predict kind of roughly what certain ant species were doing. But it just turns out that those ant species were kind of the caricatures of ants. Like they were kind of like highly stereotyped. And so they don't necessarily generalize very well, but they're kind of what a lot of people hear of kind of ants 101. And so so the basic idea here is you kind of, and I'll write this out in more detail here, but you have one ant finds food and lays a chemical trail to food. Others follow trail and reinforce. And this is a basic idea of collective intelligence. So the idea is we all don't know where, we've moved into a new building. We have no idea what food is around. I happen to find a good restaurant. I come back from that restaurant and I bump into one of my colleagues and I tell that colleague, oh, you're looking for food. I found a really good restaurant over there. And that colleague was just doing a random search, maximum entropy search, and instead decides to walk down that way. And that colleague finds that restaurant. And he bumps into another colleague who's just randomly looking around and says to that colleague, I just found a good food site over there. And so over time, you get a stream of people going to this restaurant. And the reason they keep going to this restaurant in this kind of simple model where people don't have memory is that they're actually following the trail itself. And so as you get more and more people going, they kind of become very visually conspicuous. And so we humans don't lay chemical trails, but we do lay visual trails. And so if you see that a bunch of people are going to one direction over another, then you tend to be attracted to it. And then you become part of the visual cue. And so then you reinforce that cue, and then gradually everyone's moving in that direction. Even if they don't have any information that there's anything good in that direction, they follow the social cue entirely. So it starts out as an exploration where everyone's going anywhere, nobody's communicating. And as you add more and more communication, the exploration stops and it becomes pure exploitation. So then it's just everybody's going in that direction, regardless of whether that direction's any good. So that's kind of what ant colony optimization is built on. Only I got a couple of minutes, and so I just want to lay out the basic structure here, and then we'll pick up with more detail next time. And so this is designed for combinatorial optimization. So in other words, decision variables are discrete. So that means that each decision variable doesn't come from a continuum, it's got a finite number. So it'll say each variable has finite number of options. And so what Dorigo realized in ant system, so the basic idea behind ant system, which is kind of the proto ACO, was that I can take my variables like x1 and I can represent all of its options. So here is one value of x1, one possible value of x1, another possible value of x1, and so on. So these are possible values of x1. And these aren't organized on the number line or anything, because it's just discrete. There's 5 options for x1, and these are the 5 options. x2 maybe has 3 options. x3 maybe has 4 options, and so on. So these are my decision variables, and these are the options, discrete options. And so the idea here is that a candidate solution is a path through this map, through this graph, really. You could imagine a graph where every one of these solutions connects to every one of these solutions. And so this solution connects to these 3, this one connects to these 3, and so on. And then you could have to pick a path through that graph. And so a candidate solution might be, I might choose this option, and this option. So this here is a candidate solution is a path from top to bottom. And so what we'll see next time is what's going to happen here is every candidate solution, which are random ways to go from level 1 to level 2 to level 3, we're going to evaluate the fitness of each one of those, and then we're going to put a little bit of pheromone, so it's kind of bookkeeping, based on the fitness on top of the path. And what we'll see is that good paths or good nodes to use in those paths will get a lot of pheromone on them. Bad paths will get not that much pheromone on them. And as you play multiple rounds of this, the ants will be attracted to the better paths or the better nodes. So it might be that this node, as long as you use this node, you're in good shape, even if you're using it in different paths. Well, then this node will get lots of pheromone, even though maybe some of the paths connected to it won't. And so it'll gradually refine the shape of these paths, and they'll end up getting 1, 2, or 3 paths out of this thing that are good candidate solutions. So we start out with random links all over the place, and then they get reinforced by laying chemicals, which will just be variables that we're going to add, that the algorithm keeps track of in this matrix. And then those variables will attract ants in the next round to crawl more on the ones with the higher concentrations and less on the ones with lower concentrations. And that's effectively how ant system does combinatorial optimization. And so we'll talk more about that next time, but I don't keep you any longer, so you're free to go. And we'll see you next week. So there's a Muddiest Point due this weekend. I think that's all that's due this week.
Sir, for mini project 3, can we use something like niche Pareto GA, like the one in the picture?
Yeah, there's a question about mini project 3 online. You can, as long as you're demonstrating a concept related to, let's say, Pareto optimization, then I'm definitely happy for you. Like, you can pick an algorithm that's out there, so you can say, here's what happens when we turn niching on. Here's what happens when we turn niching off. And look, the niching really does increase the diversity. So you could create like 2 optimization functions. So I guess I'll stand in front of the camera here. So you could say like, I have 2 optimization objectives, cosine X and X sine X. And so in that case, I could say I want to simultaneously optimize cosine X and X sine X. And those are my 2 optimization objectives. And so I'm going to use multi-objective genetic algorithms, or some version of it, some simple version where I do Pareto ranking. And then I'm going to try one with niching or without. And then I might see that with niching, when I actually plot my solutions on my sine X, X cosine X, or whatever plane, that with niching, I get a nice spread across the Pareto frontier, but without niching, I just get clumps. And then you could say, look, niching works. And that would be a cool project. So I don't know if that's what you had in mind, but something along those lines, I think would be fun.
All right, yeah, because the niche Pareto optimization, the GA uses technically tournament Pareto selection, and that in itself provides a little bit of niching because it keeps on just taking the dominated solutions. Dominated solutions, not dominated solutions.
Yeah, I would say that that it would be nice to have something to contrast. So if you just implement it, that'd be great. But if you could make some modification or compare it to something else, just to kind of show, I mean, demonstrating that you can find the Pareto frontier, that in itself might be, worthy enough. But I guess it would be nice if you could say, to demonstrate some concept. To me, a concept that we've learned is like that Pareto ranking works. And so how do you best demonstrate that Pareto ranking works? You could say, well, I'm going to use my niche Pareto optimization and maybe compare it to some other simpler approach. And one finds the frontier and the other one doesn't. I don't know. But I mean, it sounds like you're dreaming up things along the right direction. Simply demonstrating the algorithm is 90% there. But I want you to also then make a comment that shows, how does your demonstration actually how could I use it as a demo to demonstrate some principle that we talked about during the class?
All right, thank you very much, sir. This definitely helps point me in the right direction.
Good. Okay. Any other questions online?
Yeah, hi, Professor. I had a question. So for the mini project 3, I went ahead and implemented the NSGA2. because I wanted to work on it for a couple of time, and I thought this would be a great opportunity.
Okay.
I've been facing some issues in terms of handling infeasible solutions. So I've stuck to simple cases where I've